Up until now, we have been talking about finding extrema for single variable functions. Now, we're going to move on to extrema problems for multivariable functions. Let's look at a multivariable function f and assume that point C is an interior point inside the function's domain. When we say that the function f has a local maximum at C, it means that for any point near C, the value of the function is less than or equal to f of C. Similarly, saying that the function f has a local minimum at C means that near C, the function values are all greater than or equal to f of C. Together, local maximums and local minimums are collectively called local extrema. When a multivariable function is differentiable, we get what we call the gradient. You can see the formula for it right here on the screen. Now, the gradient is actually a vector, and its components are just the partial derivatives of each variable. Don't worry too much about the strict definition of differentiability for multivariable functions yet. We will get to that later. The main focus right now is using the gradient to find the extrema of the function. This theorem shows us that if a multivariable function has a local extremum at point C, then the gradient of f at C is either the zero vector or it does not exist. Now, a big caveat here is that this theorem only goes one way. In other words, just because the gradient equals the zero vector or does not exist at C, it does not mean that the function automatically has a local extremum there. What this theorem actually tells us is that if we want to locate the local extrema of f, these points where the gradient is zero or does not exist are simply the places where we should start looking. Points where the gradient is the zero vector or where it does not exist are collectively called critical points. Now, the points where the gradient is exactly the zero vector get a special name: stationary points. A stationary point might be a local extremum, but it does not have to be. If it is not, we call it a saddle point. This name actually comes from a horse saddle. If you picture a saddle, looking from front to back along the horse's spine, it looks like a local minimum, like the bottom of a valley. But if you look at it from left to right, where your legs hang down, it is a local maximum, like the top of a ridge. Non-differentiable multivariable functions can get incredibly messy, so we're going to skip those. Instead, we will assume that all functions here are differentiable, meaning that we only need to worry about the places where the gradient equals the zero vector. In this example, we are going to find the extrema for a function with two variables, which you can see right here on the first line. To start off, let's find its gradient, which just means taking the partial derivatives with respect to x and y, as shown in that first equation on the second line. Next, we set this gradient to the zero vector, and that gives us the stationary point at x equals 1 and y equals 4. Now, to check if this stationary point, 1, 4, is actually an extremum, we need to look at what is happening to the function values near 1, 4. We can represent any point near 1, 4 as 1 plus h for plus k, where h and k are just real numbers that are small enough. From there, we can plug this point into the function to calculate the value of f of 1 plus h for plus k, which is laid out for you in the very last line. Now, let's subtract the function value at 1, 4 from the value at 1 plus h for plus k. That is the equation you see on the second line. With some basic algebra, we can see that this difference comes out positive, as shown here on the fourth line. So, our conclusion is that as long as h and k are small enough, the value of f of 1 plus h for plus k will be greater than the value of f of 1, 4, which is exactly what the second to last line shows. From this, it is easy to see that the function f hits a local minimum at 1, 4, and that minimum value is negative 14, just like it says on the very last line. In this example, we are going to find the extrema for a function with two variables, which you can see right here on the first line. To start off, let's find its gradient, which just means taking the partial derivatives with respect to x and y, as shown in that first equation on the second line. Next, we set this gradient to the 0 vector, and that gives us the stationary point at x equals 5 and y equals 2. Now, to check if this stationary point, 5, 2, is actually an extremum, let's look at the function values near 5, 2. We can represent any point near 5, 2 as 5 plus h, 2 plus k, where h and k are just real numbers that are small enough, as you can see in the first equation on the third line. Then, let's subtract the function value at 5, 2 from the value at 5 plus h, 2 plus k, which is the equation on the fourth line. With some basic algebra, we get that this difference comes out to k times k minus h. As long as h and k are small, this expression k times k minus h can actually be positive or it can be negative depending on your choices. This proves that the function f does not hit a local extremum at 5, 2. Instead, this means that the point 5, 2 is a saddle point. This theorem gives us a test based on second partial derivatives. Let's assume the gradient of f at point C is the 0 vector. To start off, we calculate 3 second partial derivatives, which we will call capital A, capital B, and capital C, as you can see on the fourth line. From there, we define the discriminant capital D as b squared minus a times c, shown here on the fifth line. Now, if capital D turns out to be greater than 0, then point C is a saddle point. If capital D is less than 0, then point C is a local extremum. In that case, if capital A is greater than 0, the function f hits a local minimum at C. If capital A is less than 0, it hits a local maximum at C. We're going to find the extrema for the function you see on the first line. To start off, let's calculate its first partial derivatives, which are listed on the second line. Next, we set the gradient to the 0 vector, giving us the system of equations on the third line. From there, we can solve for 5 stationary points, just like you see on the very last line. Next, let's find the second partial derivatives, which are shown in the formulas right here on the screen. Next, we calculate the values for capital A, capital B, capital C, and capital D, which you can see right here on the screen. Then, by applying the second derivatives test, we can easily classify what kind of extremum each of these 5 stationary points gives us, as laid out in this table. This theorem outlines how we calculate extrema when we have a constraint. Let's say point C is an extreme point of the function f subject to the constraint that function g equals 0. What this means geometrically is that the gradients of f and g at point C must be parallel vectors. So, as long as the gradient of g at C is not the 0 vector, there has to be a real number lambda, where the gradient of f at C equals lambda times the gradient of g at C. And this real number lambda is what we call the Lagrange multiplier. In this example, we are going to find the extrema for the function f of x, y, equals x times y subject to a constraint. This constraint requires the point, x, y, to be on a unit circle, which gives us the equation x squared plus y squared equals 1. So, we can set up the constraint function as g of x, y, equals x squared plus y squared minus 1 equals 0. To kick things off, let's calculate the gradients for both f and g, which you can see right here on the last line. Based on the theorem, these two gradient vectors have to be parallel. So, there is a real number lambda, where the gradient of f at C equals lambda times the gradient of g at C. Now, for two vectors to be equal, their individual components must match. The first component of the gradient of f is y, which has to equal lambda times the first component of the gradient of g, giving us 2 lambda x. Then, the second component of the gradient of f is x, which must equal lambda times the second component of the gradient of g, giving us 2 lambda y, just like you see on lines 1 and 2. Next, let's take the first equation, y equals 2 lambda x, and multiply both sides by y. Let's do the same for the second equation, x equals 2 lambda y, and multiply both sides by x. This lets us combine them into the equation on the third line. If we plug in our constraint, x squared plus y squared equals 1, we end up with 2x squared equals 1, and that allows us to solve for x, as shown on the very last line. Following the exact same steps, we can get the equation 2y squared equals 1 and find the value for y2. Using the values of x and y we found on the previous slide, we get 4 potential extreme points, which you can see on the second line. Now, if you look at the first and fourth points, their function values both come out to 1/2. On the other hand, the second and third points both give us a function value of -1/2. So, we can conclude that the maximum value is 1/2 and the minimum value is -1/2. In this example, we want to find the minimum value of the function f of x, y, along the hyperbola x squared minus y squared equals 1. Clearly, the values of this function can go all the way to positive infinity, which means that there is no maximum value here. This hyperbola is the constraint, so we can set it up as the function g of x, y, equals x squared minus y squared minus 1 equals 0. To start off, let's calculate the gradients for both f and g, just like you see on the very last line. Based on the theorem, these two gradient vectors have to be parallel. So, there is a real number lambda, where the gradient of f at c equals lambda times the gradient of g at c. This means that the first component of the gradient of f is 2x, which must equal lambda times the first component of the gradient of g, giving us 2 lambda x. Then, the second component of the gradient of f is 2 times y minus 2, which has to equal lambda times the second component of the gradient of g, giving us -2 lambda y, just like you see on lines 1 and 2. Now, because the constraint x squared minus y squared equals 1 forces x to be something other than 0, we can just cancel out x from that first equation. 2x equals 2 lambda x. That immediately gives us lambda equals 1. If we plug this lambda equals 1 into the second equation, 2 times y minus 2 equals -2 lambda y, we can easily solve for y and get 1, as shown on the very last line. Now, if we plug this value of y equals 1 back into the constraint, x squared minus y squared equals 1, we can easily find the value of x. That gives us 2 extreme points, which you can see on the second line. Since both of these points give us a function value of 3, we can conclude that the minimum value of the function is 3. In this example, we are looking for the maximum value when we multiply 3 variables together subject to a constraint. This constraint requires us to be on a unit sphere, and all the variables have to be positive, just like you see on the second line. Now, it is pretty clear that the minimum value here is 0, so we only need to worry about finding the maximum. Let's convert the unit sphere equation into the constraint function g shown here on the third line. To start off, let's calculate the gradients for both f and g, which are listed on the very last line. Based on the theorem, these two gradient vectors have to be parallel. So, there is a real number lambda, where the gradient of f at c equals lambda times the gradient of g at c. This means that the first component of the gradient of f is yz, which must equal lambda times the first component of the gradient of g, giving us 3 lambda x squared. The second component of the gradient of f is xc, which has to equal lambda times the second component of the gradient of g, giving us 3 lambda y squared. And the third component of the gradient of f is xy, which must equal lambda times the third component of the gradient of g, giving us 3 lambda z squared, just like you see on the second line. Next, let's take the first equation, yz equals 3 lambda x squared, and multiply both sides by x. Let's take the second equation, xc equals 3 lambda y squared, and multiply both sides by y. Finally, let's do the same for the third equation, xy equals 3 lambda z squared, and multiply both sides by z. By doing this, we can combine all of them into the equation on the very last line. If lambda is 0, then looking at the equations from the previous slide, we can tell that at least one of x, y, or z has to be 0. That would make the function value 0, and we know 0 won't be the maximum. So we can safely assume that lambda is not 0. In that case, using the very last line from the previous slide, we can cancel out lambda and end up with x cubed equals y cubed equals z cubed, which you can see on line 3. In other words, x equals y equals z. If we plug this into the constraint, x cubed plus y cubed plus z cubed equals 1, we can solve for the values of x, y, and z, just like on the last line. And that gives us the final maximum value of 1/3.